In this paper, we conducted a comprehensive suite of evaluations, known as BOB, to identify the top-performing backbones for computer vision tasks. The models that consistently outperformed others across various tasks, datasets, and settings, including in-domain, ID, and out-of-domain, OOD, scenarios, were supervised convex-based, supervised SWIN v2 base trained using ImageNet 21K, and ClipVit base. These models also performed well at smaller scales, with convex tiny and SWIN v2 tiny emerging as the top performers among smaller backbones, followed by DinoVit small. We found that supervised pre-training with convolutional neural networks, CNNs, outperformed transformer-based architectures and self-supervised learning, SSL, models on the majority of tasks considered in the evaluation. The superior performance of supervised pre-training can be attributed to the availability of models trained on larger datasets. However, when compared on the same dataset scale, SSL models performed better. Our findings also revealed that vision transformers, VITs, were more sensitive to the amount of pre-training data and the number of parameters compared to CNNs. This suggests that the performance of VITs is influenced by the scale of pre-training. Furthermore, we observed a strong correlation in performance across tasks in BOB, indicating that the top-performing backbones tended to perform well universally across different tasks and settings. We also referenced previous benchmarking works that compared different pre-training routines and architectures. These works found that supervised learning models consistently outperformed SSL models. We highlighted the progress made in pre-training algorithms, training sets, and architectures since those previous works. The evaluation in BOB included tasks such as classification, object detection and segmentation, out-of-distribution generalization, and image retrieval. We measured the performance of the backbones both in fine-tuned and frozen settings on these tasks. We acknowledge the limitations of the evaluation, such as the use of publicly available checkpoints that may have been pre-trained with varying amounts of hyperparameter tuning. However, we believe the comparison of existing checkpoints is relevant for practitioners as it represents realistic conditions.